MestreCast, analytical chemistry software in a fast-changing world with Santi Dominguez.
Just as a bit of a reminder, here we are talking chemistry, we are talking processing analysis, we are talking automation. And the first episodes, we've been talking with members of the Mestrelab team. We will extend on that to include customers, etc. later on. But today I have with me Dr. Kate Kemsley, who is coming to talk to us about AI modeling, the next frontier in chemical space. Hi, Kate. How are you doing?
Hi, Santi. Very well, thank you.
And where are you joining the podcast from?
I'm joining it from my office at the University of East Anglia in Norwich.
Okay, all right, very good. What's the weather there like? It actually looks sunny. We're actually on Teams, and it looks pretty good. I'm in Spain, and it's raining. You know.
No, you've got just the half an hour that the sun's come through. We've got terrible weather. It's cold, and it's been raining for about the last fortnight non-stop.
Well, I'm sorry to hear that. Luckily, we that's not a problem we are trying to tackle with our technology. We are keeping it to the more simple world of chemistry. Yes. And Kate, thank you very much for joining us. I think I'm really looking forward to the discussion today. Maybe just as a bit of an introduction, you joined Mestrelab in October as a scientific director, October of 2023, right? A few months ago. So can you maybe start by telling me why that happened? What attracted you to the role?
So I would say that one of the most exciting things for me was joining the Mestrelab company environment. It was a huge attraction to know that I'd be surrounded by highly skilled colleagues who I can really engage with, and we're all working towards the same goals, really. It's interdisciplinary, so I have a physics and statistics background, but I'm working directly alongside chemists, spectroscopists, coders, developers. We make a really diverse team, but still sufficiently close scientifically to speak the same language. And I feel that really helps in learning from each other and helping the sum of all of us to be more than the parts, really.
Okay, and within that, let's call it environment or universe, you are focused on data processing, on the data processing side of things. Can you tell me a little bit more about what's going on there?
Yeah, sure. So before joining Mestrelab, my main field of work was as a computational statistician, and I mostly handled data collected using analytical technologies, so including NMR, but mass spec, and other things as well, proteomics data, imaging. And the raw data from all of those always needs some basic processing to extract information in a useful form. But as the instruments have become more and more high throughput with autosamplers attached, for example, so we're getting larger and larger amounts of raw data, huge quantities. And this is causing bottlenecks at the data post-processing stage. It's really fair to say that human oversight is really still needed, and it can be time-consuming, tedious work. But actually, addressing that with full automation is really hard. All those data handling steps, they still need somebody to check over them to make sure it's all going properly. And it's going to be my role within Mestrelab to look at some of the ways that we might be able to meet those challenges.
And I think those challenges are very important because we as a company think very much about accelerating our customers' research efforts. And when you look at the research these days, I think, for example, in the pharmaceutical industry or any of our target industries, we talk about bottlenecks a lot. It's interesting that on the second question, you have already mentioned the word bottleneck. I seem to be forever talking about removing bottlenecks. And a lot of bottlenecks come from an analogical origin. You know, they are related to humans having to still analogically put eyes on data, make decisions, etc. So I'm very much aligned with what you're talking about there. I think if we could remove that dependency, we will be able to do things much faster, and that would ultimately result in getting treatments to market quicker, getting new materials faster. That can really have an impact on people's lives. So it's a very worthwhile aim, a very interesting project, I think. And I would be very keen to hear a little bit about what research you are currently working on. So what's within that large statement you have made, what are you actually specifically doing as we speak?
Right. So right now I'm working on a method for automated chemical shift prediction in NMR. That's for aiming ultimately for assignment and verification of NMR spectra. And to do that, I'm using a really quite new AI approach. It's only been around for a few years. 2017, I think the first paper came out that mentioned this in this context. And that uses something called message passing neural networks. So they're a form of convolutional neural network, and they're very well suited to dealing with information represented by a network or a graph. So it's not a neural network, that's a network in the graph sense. So that's nodes and edges connected together. And molecular structures are a very good example of that kind of data. So very amenable to being treated with message passing neural nets.
Great, and I've read a few papers in which molecules are very much referred to as graphs when you think in the context of artificial intelligence. It's a very interesting application, and I mean we've been predicting a spectra for a very long time, right? We've been trying to verify a structure by NMR for quite a long time, and predicting a spectra for much longer, probably since I would say maybe the 70s. So it's fascinating to see such a modern, newly developed technique being applied to a problem that's been around for quite a while, and that has been tackled in a number of ways already in the past. So could you elaborate a little bit more on what message passing neural networks, what they do, how they actually work?
Yeah, so how they work is that they utilize both the connectivity pattern of the molecule at the same time as the features of individual atoms in the molecule. So each node in the graph holds the feature information. So that's things like atomic number, valency, hybridization state. So that's things that are important for determining what the ultimate chemical shift will be. And in the message passing step of the neural net, those two sets of information, so the connectivity and the node features, are multiplied together. And that has the effect of smearing out the atom's information across its nearest neighbours to give a kind of updated feature set. And you can control how much that smearing happens. So if you compare it to the kind of quantum mechanical methods, which we've been using previously, it's similar, but there's a little bit more flexibility and learning from real-world data rather than using fixed physical rules. And we found that makes very good predictions of chemical shifts. Really, the precision and accuracy of the chemical shift precision is better than anything we've seen reported in the literature previously. So actually, we're moving to embed this in our existing software for release over the coming months.
And that's really cool, Kate. I'm delighted to hear that this is actually going to make it into the product that our customers use in the short term, right? Because I think when you look at these new technologies and you tackle a new problem with them, initially that is it's quite a research effort, right? And a research from the perspective that you have no idea of how long it's going to take to solve it and whether it is actually going to be useful or not until you actually run it, do the work, and see what the results are. So I think that's great, considering that obviously you joined in October, so we haven't been working at it for that long. And since this is making it into the product, and I guess it will be in Mnova and related products, who do you see the tool appealing to? Who do you think will be the end users that will see the most value from what you're currently doing?
Well, I would feel that a highly accurate prediction and assignment tool would be of interest to researchers, chemists, any professionals working with NMR spectroscopy, really, to check products of synthesis. Or if we're good enough in terms of prediction, it would help with unpicking spectra of complex mixtures. I feel that could be a really exciting new development if we get a sufficiently accurate prediction tool.
Yeah, and in fact, complex mixtures are not called complex for nothing, you know. So
no, exactly.
We've been grappling with that problem at the Mestrelab for a long time, and even though I will say we have some partial solutions and we've made incremental steps, it's certainly an area where a lot more could be potentially achieved. So, I'm very curious as to seeing how message passing neural networks, I need to get used to this, perform in that context. And of course, our users will see a result, Kate, and that result may be great. You've already alluded to how powerful it is for the actual prediction of NMR spectra. But a little bit like with excellence in sport, we see a fantastic final product. We don't necessarily see the difficulties and challenges that have got us to that point, right? So can you comment a little bit on the kind of challenges that you have encountered, if that's the case? I would assume probably it is, but have you encountered any challenges along the way?
Yes, I have. Setting up the neural network architecture took quite a bit of time. In all neural networks, there's a lot of hyperparameters to choose. So that's things like the number and type of layers, the learning rate, the batch sizes, the number and type of features to use, how to normalize them. There's really quite a long list. And there's no quick fix to knowing what those answers are. It's really just an element of trial and error to tweak things and see how you get on. Putting something together that sort of works is quite easy, but refining it so that it really works well and brings down the error, that's a lot harder. And it's not only just getting the performance, it's also getting it in an acceptable training time. And that's not so straightforward. So I've had to use really quite some hefty computing power to do this.
Okay, that's very interesting. And of course, yeah, the ultimate challenge comes from the fact that you are trying to improve on a state of the art, which has already been developed for a long time, right? So it's not a task for the faint-hearted, I would say. Okay, so obviously quite a significant design and parameterization effort, computational power, and any other challenges?
Oh, yeah, I suppose, as you say, handling a large size of data set, that's been difficult. You probably know that deep learning has this requirement for massive amounts of labeled data. In my case, I've had to work with tens of thousands of accurately assigned NMR spectra from various compounds, a big diverse data set. It's crucial to note that data is really well curated. It comes from within Mestrelab. It's not just scraped off the internet, but we really have to have huge numbers, so tens of thousands. So that's just a difficulty in handling it on my desktop PC, let alone transferring it across to a high-performance cluster for actual processing.
Oh, okay. And why is this important? Okay, the size of data, the data set, etc. Why is it so important?
It's really because artificial intelligence methods aren't exactly smart in the traditional sense. They learn the huge numbers of parameters through repetitive processes on vast amounts of training data. So if there are errors or inconsistencies in the data, the model will learn that too. And that's quite different from models based on clear physical rules, which might be better at identifying certain kinds of anomalies in the training data. We're not in that situation. Instead, we want to learn from real data so that where the physical laws might break down, we're in a better position to predict outcomes for that type of data. But to do that, we really need lots of good examples, good labeled data to work from in the first place.
And hence the importance of the curation and obviously also the risk of just taking a data set scraped from the internet. I guess the old adage, garbage in, garbage out, very much operates in this context, right?
It's exactly that. We do want unusual cases, but they do need to be real, not just labeling errors or typos, but genuine deviations from expected physical rules, because, exceptions are always going to be there. And I suppose a good comparison would be with the large language models that we're all hearing about now, ChatGPT and so on. They don't rely on a predefined set of grammar rules. They develop their own language through extensive training on real-world text that has been scraped from the internet. And that's why they're so good at mimicking human language, even including informal speech and dialects and slang and so on, so they can cope with exceptions to the rules. And that's what we want to be able to do as well.
And that's obviously a very exciting and somewhat ambitious analogy, right? Because the way large language models have moved on the field of natural language processing, etc., in the last year or two, I think hasn't been missed by anyone. It's mind-blowing in many ways. And it's possible that being in the field, you had seen it coming. I think for most people, for the man on the street, what happened with, probably I would say ChatGPT was the first one, right? There are other vendors available, of course, but that very much changed the way we think about AI and natural language processing. And it's fascinating to read some of the statistics about adoption speed, how fast it got to 100 million users compared to the internet, to mobile phones and everything else. But today we're talking about chemistry in the context of AI rather than ChatGPT. So I want to go back to maybe, and this is a little bit, I think the way I always think, which is good and bad in many ways. But as soon as I hear about something that's working and something that's going well and something that moves the field along, my next question is always, so where next for the technology, Kate? Let's assume that we succeed in the current project. It sounds like it's going pretty good and you're already getting results that are worth including in our products. So where do you see maybe the ultimate applications or the ultimate potential of the tools you're working with?
I would say my holy grail would be that we can extract something new from a natural product, some completely unknown compound, because after all, we know that the amount of chemical space that has been discovered by humans at the moment, the number of compounds out of all the possible small molecules, for instance, is a tiny, tiny percentage, fraction of a percent only. So suppose we've got some new product that we've found in a plant picked in the Amazon, discovered in the Amazon and extracted some compound, and we take an NMR spectrum and a mass spectrum and we don't know what the compound is. My ambition would be that using tools, we can collect spectra and go backwards and say what that compound is definitively, forensically, not just a guess, not just some part of the structure, but all of it. And quite a complex molecule as well. I'm talking about, a largish small molecule. How do you discover backwards what all the different features of it are? Or perhaps working from proposed molecules where people have synthesized computationally new potential compounds that might be useful in some context. Can we synthesize them then in the lab and work out whether we've got the right thing? Again, all of these tools which can do elucidation, which can go backwards from recorded spectra computationally to saying what the structure we're looking at really is, that would be my holy grail.
Okay, very interesting. Yeah, which is what we exactly traditionally refer to as structural elucidation. I always have a smile when I hear about that subject because it always reminds me of a movie with Sean Connery I think it's from the early 90s. I'm trying to remember the name now. It was translated to something weird in Spanish, but I think in English it was probably something like Medicine Man. And in this movie, Sean Connery was a scientist who was in the Amazon, and he found a new extract from a plant and just put it in a little machine, and the machine told it the structure and properties and everything else, and
there you go. That's it.
That's exactly what we're aiming to do here, right? Unfortunately, we don't have Sean Connery, so we have to do it for real. And that is not quite as simple. So it's not a 1992, but maybe 2025, 2030. What would you say?
2025? I'll be optimistic.
Wow. Okay.
2026.
Well, I actually think that's a very exciting answer. Kate, so great. And I think one thing that for me is interesting as well is that you come, we're used to talking to people who have spent their life in the NMR community or the mass spec community, depending on which field we're specifically talking about in this podcast and also in our everyday life in Mestrelab, since this is where our DNA really is. But you're a little bit of an outsider from that perspective, right? And yes, maybe it would be interesting, obviously, because you bring something very new, I think, to the way we approach these problems. You're one of the Mestrelab ways of thinking outside the box. Maybe I will put it that way. So I think for the audience, it would be very interesting to hear a little bit maybe about the professional journey that's led you to this point. So, maybe starting with, where did you go to university? What did you study? What research did you do? And what was the subject of it?
Okay, so I originally went to Oxford University, where I graduated with a degree in physics. And after that, I did a few years of patent examining in the field of modern optics. But I found that very dry, actually. I really needed to get back into a lab.
maybe large language modeling may have helped quite a lot there and made it more interesting if it were available at the time, right? But obviously too early.
It was too early. We were only just, when I left the patent office, we were only just starting to use PCs for search to help in our search examining.
Okay.
But anyway, I don't think that would have made the job any better, really. So that was too dry for me. I needed to get back into a lab. So I moved back to the UK and started an academic career at the Institute of Food Research. Initially, the subject of my research there was spectroscopy. So it was mostly infrared, Raman, a little bit of NMR, and that was for food composition applications.
Mm-hmm.
But very quickly that developed into doing chemometrics because that was emerging as a promising new field in the 1990s. And the Institute of Food Research sponsored my PhD, and that was in computational statistics and machine learning. So I actually started even back then doing some genetic algorithms in the 1990s. They don't bear much resemblance to what I'm doing now, but it was the starting point. And I've remained active in that research field ever since, really.
Yeah, fantastic. So that I think that gives us a little bit of an idea of the perspective that you bring into this effort. So maybe one final question from me, Kate, which is what drives your enthusiasm for data analytics? You obviously look at it in a I think it comes across very easily that you look at it in a very different way to patents reviewing. So what is it about it that drives your enthusiasm?
I just find it a really exciting ride, actually, with accessible computing power still continuing to increase. We've got quantum computers on the horizon. It allows us to constantly push at the boundaries of what we can actually do with our data sets. That I think is that evolution of the field of computational statistics, because that's what I see neural networks and machine learning as a branch of. That evolution is what really keeps me enthusiastic about the field. And that's really why I joined Mestrelab. I want to use this knowledge to help keep the company at the cutting edge of analytical data processing.
Well, that sounds great. And we do want to be at the cutting edge. So, from that perspective, it's a great fit. So, guys, there you have it. And we have it hot off the press from Kate, automated structural elucidation in 2026.
Yeah.
Kate, we will have you back to talk about it once we've done it. I won't hold you to the date, but I really hope that you're right. I will watch the journey and the potential of not only message passing neural networks, but of artificial intelligence approaches in general with great interest. And it's been great to have you. Very interesting. I've learned a lot. And I'm sure we will be sharing some more episodes of the podcast later on. So since we're recording on Friday afternoon, I want to wish you a very good weekend. I hope the weather improves somewhat for the Saturday and Sunday. And thank you very much for your time.
You're welcome, Santi. Thank you too.
Take care. You can find all MestreCast episodes at iVoox, Apple Podcast, and Spotify. And you can, of course, follow us in our Mestrelab media channels on LinkedIn, X, Instagram, Facebook, etc. So please follow us, share us, and we look forward to seeing you attending future episodes.